heat flow models for Antarctica.
Yeah, thank you, Marijn. Welcome back. I tried to give you a flavor of where we are in terms of geothermal heat flow for Antarctica. And I have to acknowledge a lot of co-authors and cooperators, as you can see here. So most of the work has been done by the students, and I just have the pleasure to present you the results. I start with Greenland. So I start with Greenland, and in Greenland, in between, we go to Antarctica. So this picture is nicely illustrating where the problem is with geothermal heat flow, or what is the contribution to basal melt from heat flow. You can see here, G, that's geothermal heat flow, and in Greenland, it's about 1/4 of the contribution to the basal melt rates. So that's not the main contributor, but it's the main uncertainty in these models. So actually, from the uncertainties in the order of 20%, and these 20% are coming from the geothermal heat flow models because that's the least constrained. And why? You can see here, these are the different heat flow models which are existing for Greenland. Not all of them, actually even more, but it's just the most recent. And you can see that, for example, for the northeast Greenland ice stream, we have 1 gigaton here, we have 1.5, even up to 2 gigatons. So there's kind of 50% uncertainty at least. And it's just depending which of these geothermal heat flow models you're using. What Nana Carlson in her study has been doing, she used an ensemble of the models, which just means she used an average of the different contributions because there was not clear how to decide which is the best model, which is the most reliable model. Now, for Antarctica, the situation is similar. I just show 4 models. There are far more models that you can find in literature. These are, I would say, the 4 most recent models. 3 are based on kind of empirical, machine learning, similarity, multivariate similarity analysis. The advantages are models which are based on multiple data sets, and you make a statistical correlation between observed heat flow points, and there are only a few available. So that's the problem. And on the other side, you have these models which are, for example, based on magnetics. Like here, a famous model from Yasmina Matos, using Curie depth analysis, and then you get 1 point, and then from the point that you get, you calculate the heat flow by assuming some radiogenic heat production, some parameters in the crust. So you estimate this point, and then you have to find some parameters. And what you do, you calibrate it at the boreholes, a few boreholes available, and try to link it. And you assume maybe that there is a change between West and East Antarctica, but otherwise the parameters are constant. So in these models, everything is constant, for example, for West and for East Antarctica. This explains the differences between this model and the 3. And I will mainly speak now a little bit of the 3 models based on this similarity analysis, because they are trying to converge quite nicely. So here is showing the differences between these multivariate models, and you can see that the overall pattern is quite similar. There are still some local differences, but overall it seems like we get an agreement between the different models. So that's actually a step forward. Before, like 10, 15 years ago, models were really converging in different directions, and main differences between the models, actually the data sets are used. Maybe some of them use older data sets. But in a new model that Tobias is now developing, I think we're getting more and more to a more common model. So problem solved? Not really. The problem is then, of course, that we don't see the local variation that we really needed, and Alan has addressed this in his talk before, that for having a reliable model for ice sheet modelers, we need higher resolution in the models. So these models have maybe 50 to 100 kilometer resolution, so really nice for the continent size, but they're not really of interest or not really useful for the size of an ice sheet. So this is also illustrated here from the paper from Anja Redding, a nice review paper, which I really urge you to read. And you see we have all these contributions to heat flow that's supposed to be heat flow, and then you see kind of the interpolated envelope. That's maybe what we tried, that we can resolve at the moment. But of course, we would need all the different details to really address how the evolution of an ice sheet is. And there was a nice study by Felicity McCormick showing how if you introduce some local variations has a huge impact of how the ice sheet is developing. Good, so we can go home and stop there because the models are not useful, or maybe we try to do something else like Alan suggested. But we can also use other types of information, and this is actually something which is coming up in recent years, and there will be a dedicated talk to this. It's actually getting ice temperature models, and Catherine has a talk about this, and there's a nice poster by Marion Leduc-Lebalieu, And it explains using data from the SMOS, the soil moisture and ocean salinity satellite mission, to actually get ice temperature models. So the idea is now we're getting from the top to the bottom, and then we somehow have the interface here where the models should meet. And that's now the challenge, I think, for us. We get reliable, hopefully reliable models in the near future of the ice temperature, and we have solid Earth models, and we have to marry the two models to get a common model. And I will just show you some ideas how we propose to go in this direction. It's not the final results, and they're actually still calculating because, well, Bayesian inversion, what we're using, is quite computationally demanding. Now, the problem at the moment is that's one of the outputs from the SMOS geothermal heat flow. So geothermal heat flow is there used as an input with a low, with a high uncertainty. So you can disturb the model quite a lot to fit the ice temperature. That's the model from Tobias Dahl, and that's the differences in between. And you see here all range of plus minus 40 milliwatt per square meter. Of course, the question is this an artifact between the two inversions, or is this geology? I don't think it's geology. I think it's still that this model is probably too less constrained, and we have to really get a closer fit. But there seems to be also some details which are true, which should be introduced in our regional scale models. One problem still is the limiting factor is the low sensitivity of the SMOS inversion to the deepest ice layer. And there's actually now a new proposal for a new satellite mission, the CryoRAD mission, to actually get a new radiometer system to actually get better temperatures at larger depths, both for Greenland and Antarctica. And if this would fly, we'll see if this is selected. Maybe in 10 years, we actually get better models with higher resolution. It's also shown here, that's one of the first approaches, is the Robin profile, and this showing you a borehole, more or less, and the yellow line is the in situ, and the black shows what the SMOS inversion is giving them. So what we tried at the moment is actually get a better, closer fit to the in situ data, to the borehole data. Catherine will show another approach. We actually tried to marry our solid Earth model. That's what work that Marine has been doing before she left to Australia. Trying to use our lithospheric scale model that we have, defining input parameters and likelihood on the existing models. Then we try an iterative adjustment of the priors to kind of getting closer fit so that the prior, both from our models and from this ice sheet models, are getting closer to each other. You get an updated posterior distribution, and what you get at the end is actually, and I take this away, a better fit to the borehole data. So that's with the model from Stoll et al. And you see here with the wide range, we're getting quite far away. There's still a mismatch, which also has probably to do with the resolution of the models, but actually we're converging towards something which is also in alignment with the borehole data. And the same story we are trying to do for Greenland. The same story we're also trying to do on a larger scale for Antarctica. But I think Marion tells me since 4 months that the model is still calculating, so we still have to wait until the final results. But maybe at the end of September, I was told, she can show some new results. But it's very exciting, I think, that we have now an ice temperature model, and we have solid Earth models, and we're getting close that we can fit. And I think that's the feedback between the two domains is the most important point. I can give you another example. So we go back to Greenland, where we did another test, and this is where we have a profile, an airborne profile actually. We're just going from here in the north to the North Grip Station. This is from the study from Yadem et al. We used this ultra-wideband microwave radiometer, which is used as a test case also for the satellite mission, showing you nicely the temperature distribution, and we get also a variation of the basal temperature for this profile. So we have a new heat flow map, which has been based also on a multivariate machine learning approach published by Colgan et al. We also have a new lithospheric scale model that we put together in the last months. There's now a paper by Agnes Wansing, which has just been submitted for publication, showing a little bit the geometry of the model and a nice 3D illustration. And we can now try for the profile to see how we can actually marry the temperature data and our lithospheric scale model with this given heat flow model, I have to say at this stage. I show you next picture more results. This is just showing you the heat production, and you actually see, and this heat production has the largest effect on getting an agreement between the ice temperatures and the profile, whether the solid Earth and the ice temperature profile. That's reasonable, geologically not completely unreasonable, but of course one needs more in situ data to really constrain that having a high heat production province here is realistic, so we can have a look at magnetic data to actually make a further adjustment or further judgment on the model validity. Bayesian inversion, you get a lot of these kind of heat plots and so on. There's a nice correlation between the radiant heat production and the surface heat flow. That's what I said already. Also between the mantle heat flow and the LRB depths, that's kind of what is accepted. Crustal conductivity it seems to be more difficult to catch for the inversion. And this is kind of still, we have radiogenic heat production and crustal conductivity. Both parameters are important. At the moment, inversion seems to use the heat production and ignore a little bit the conductivity. So I think more data in the future would certainly be helpful, or more analysis where this is coming from. What is still missing is an iterative refinement of the geothermal heat flow model. So at the moment we try to match, but actually we should also adapt and change the heat flow model. And for this I come back to the magnetic data. So magnetic data would actually help, because magnetic data show us the relative changes. So even if we say that on a continent scale maybe the models are not reliable, but like the Curie depth estimates, if you do local calibration, they can be very useful to add this resolution that Alan was asking for, to actually get a better resolution heat flow model, which we can test. And that's what we're currently doing for Greenland, looking at the onset of the northeastern Greenland ice stream, how much this heat flow models and the implications actually change. What is also nice, and I don't show you here, is actually that we have some other heat flow models which you could rule out, because then you get completely discorrelation between the parameters, and it certainly is that the models are not plausible. So at the moment we can at least make a statement that models are plausible. They may be not correct, but plausible. And I think that's a step in the right direction to better improve heat flow. Okay, Marine is standing up. I just showed a summary slide. I think we have an overall idea about the regional heat flow, the baseline. We need the details, and I think that's the challenge for the next years, to really, for us geophysicists, to get higher resolution, merge different data to get better and more reliable heat flow models to the community. Thank you.